Morning.
We are starting on chapter 19. We're going to do a little bit of nomenclature. So we're dealing with aldehydes and ketones. These are going to be our highest priority groups. Aldehydes actually get a trump ketone. So in terms of naming priorities, our number one is now aldehydes. Followed by ketones. Followed by alcohol. Alkyne, alkene. And then lastly, any sort of like halogen or methoxy or carbons are all in this bottom group. Okay, so how do we name an aldehyde or a ketone? Our suffix for an aldehyde is going to be Al, and our suffix for a ketone is going to be O-N-E, which is both kind of, derived from their names. So if we have something like this here, where we have, let's see, 1, 2, 3, 4, 5 carbons, this would be a pent, and and then for aldehyde, you're going to end it with Al, so pentanol. Alternatively, for some sort of a ketone, like this here, we're going to indicate which position our ketone starts on, going for the lowest number we can. So 1, 2, 3, 4, 5 here. This is going to be a 2 pent and own, so O-N-E. Let's do an example where we have both. Well, honestly, let's do a more complicated one. We're just focusing on ketones. I'm not that worried about getting both of them on there. Nope, not that. So doing a more complicated example. Of a ketone. So taking a look at this molecule here, we have a 6 when we're doing, which would be a cyclohexane. It has a ketone on it, so this would be a cyclohexanone. We've got, oh, and then our numbering is always going to start with that the ketone when we're doing rings, because you always want to prioritize your ketone because it's our second highest priority group here. So this would be 1, 2, 3, 4, 5, 6 here. So on 2 we have an ethyl. 3 we have methyl groups. 4 we have a chloro. Doing some RNS. Take a look at the center number 2. This side of the oxygen is going to be our highest priority. Second highest to be the other side where we have all these carbons. Third here, we are going counterclockwise. This should be S. Let's see, chlorine's highest. Side with these methyls. Rest of our ring, also S. If we were to put this all together, 2S, 4S, ethyl would come, oh, chloro would come next, 4 chloro, 2 ethyl, 3 dimethyl. I'm gonna run a space down here. 1 cyclohexanone. All right, so same concepts as you've kind of been doing before. You can just kind of do a couple of these, smash them together. All right, let's. There's a question in the chat. We got to split up cyclohexane. Yeah, you could also write it as cyclohexane 1 own. That's another option. Let's start to talk about some reactions from this chapter. So there are a lot of mechanisms in this chapter, but they're all very similar. They're all going to follow the exact same pattern. The first step of these is all going to be identical. So the first reaction we're going to do is H plus in H2O. This is going to end up making a diol here. Now the way that this is going to work is that we are going to pick up a proton from our carbonyl. And this is a step that we're going to do in every single reaction we have in this chapter, or at least the vast majority of them. And this is going to make our carbon center even more electrophilic. So we have another resonance structure here. Where we have a positive charge on this carbon. It's very easy to attack at this point. So in water, our water can come in, attack at our carbonyl center. Another water can pull off a proton. In order to make this proton catalytic. And that's going to get us, I guess, storage one over there, to our final product. Also, all the reactions in this are going to be reversible. So removing water from this reaction is going to let us go in the opposite direction. And that's going to be useful when we get to some of these further down the road reactions. Okay. Okay. Our next reaction is kind of where we start actually doing things that are generating useful products. So if we instead add an alcohol into solution, so assuming H plus, let's take ethanol. Our first step is going to be the same. We're going to grab an H plus. To protonate our carbonyl here. From this point, our alcohol can come in and do a nucleophilic attack. Another equivalent of our alcohol can come in, pull off that proton. And we're going to get to kind of a halfway point in our reaction. This is going to generate what's referred to as a hemiacetal. Someone asked me if this reaction has stereochemistry. It does not have any stereochemistry. All right. From this point, we are going to transfer that proton we just picked up to our alcohol. I'll kind of explain what a hemiacetal is once we make a full acetal. All right, so we made water, which is a good leaving group. Our ether here can come in, kick out the water. A second alcohol can come in. And we can lose this last proton. To generate what's referred to as an acetal. So we've essentially made two ethers at one center here. If we take a look back at our hemiacetal was the point where we made one ether. And then we still had one alcohol, versus our full acetal is where we have both of them. So similar to, let me just draw that out. Give you guys a second to get caught up. Our H plus and H2O. Which made this gem diol here. When we have H plus and an ether, so H plus and an alcohol, we're going to make this acetal, which is just two ethers coming off the same position. So similar concept, just quite a few more steps to it. The next thing we're going to do is going to be using an acetal as a protecting group. Although I don't know how much protecting group theory we're going to get into today. If I take a diol here, so instead of having two equivalents of alcohol, I'm going to be able to do both of these reactions with the same molecule. And I'm going to be able to generate a cyclic acetal out of my diol here. So there's 3 carbons. Now we're going to make this structure here. So we're going to take a second to walk through this mechanism, which is essentially identical. We've just added, or we've reduced the use of 2 alcohols. We're just going to use the single one. Redraw that at the top. So our mechanism, we are starting off with, as always, attacking this H plus here. We are going to protonate our carbonyl. From this point, our alcohol can come in and do an attack on our carbonyl center. I'm going to draw this the shorthand way, which is just having this alcohol directly transfer it. So we're going to pick up this H here. From this point, we can kick out the water. Generate this carbonyl-like compound here. Our other oxygen can come in, do an attack at this center in order to make our cyclic acetal. Still going to have one proton on there, so we need maybe the water we kicked out to come in and grab that. In order to give us our final product. So identical mechanism to what we talked about before. The only real difference is that yeah, you could either have your starting alcohol do this last step, or you could have the water. Either of them would be fine. They have very similar pKa's, so it's not going to be that selective for one over the other. All right. So a little bit of a review. H plus H2O can get us to a diol. When we have an alcohol and an ether, sorry, H plus and alcohol. We can make an acetal. When we have a diol, Let's do a smaller ring this one. So there's only 2 carbons in between now. To give it this structure. I'm gonna throw 2 more in here that have identical mechanisms. So if I use a thiol, I can make a thioacetal. Or if I use a dithiol, I can make a cyclic thioacetal. The thioacetals, or the cyclic thioacetals, are going to have an interesting feature to them. Is this going to allow us to fully reduce off a carbonyl down to just carbons? You don't necessarily need to know the names. I'm just writing them out because I like to say them a lot. So you're not going to have like a nomenclature question where you have to label them. Yes. So if you take a cyclic thioacetal, we can throw in something referred to as rainy nickel. And this is going to reduce this down to just carbons. This is particularly useful because we don't really know a way to do this. Really, at this point, all we know how to do is take a carbonyl, throw in something like LAH to get an alcohol. We don't have a way to get completely reduced down to the carbon, just carbon here. So using this dithiol followed by rainy nickel will allow us to do that. I'm going to talk through a couple more reactions and then we're going to take a little break. So we're going to kind of finish off the reactions that follow this series. The next two are dealing with nitrogen. And we're going to make what are referred to as amines and enamines. So if we add in a primary alcohol or just ammonia, we're mostly going to talk about a primary alcohol. So primary alcohol will be something like ethylamine here. It's got 2 hydrogens on it and 1 carbon substituent. This is going to end up making us what is referred to as an imine. And then if we have, so this is primary, a secondary amine, So now we have two substituents on our nitrogen. This would be a secondary amine. We're going to make what's referred to as an E-amine. All right, so let's talk through these mechanisms a bit, and then we will take a break. Starting with our imine. It's going to be a pretty similar mechanism to what we were talking about before. We are going to pick up a proton on our carbonyl. This is always our first step. From here, our nitrogen can attack. Someone asked how many mechanisms will be on the upcoming exam. It's going to be 2 mechanisms, because this is a pretty mechanism heavy chapters. All right, we're going to do a transfer. What?
The 2 questions completely will be about mechanism.
Yes. I'll go over that tomorrow, what the exact format will look like. We're going to transfer a proton to our oxygen. Kick out this water here. Generate a protonated version of our final product, and then we can pull off another proton here to generate our imine. So nitrogen is a little bit more stable than oxygen in this form. There's no charge on it, which is why we don't have another nitrogen coming in and attacking. This is actually a stable product for nitrogen. This is going to change a little bit if we have a secondary amine instead of a primary one. So making our amine a little bit bigger. First step's going to be the same. Picking up a proton here. Nitrogen can come in and act as a nucleophile. From here, we can pick up a proton. Kick out our water. And generate our imine. Well, technically our protonated imine, although there's no proton in this case. Okay, so if we compare this to where we were a minute ago with a primary amine. Oh wait, I'm forgetting some parts of this molecule. When we had a primary amine at this point, we had this proton here we could easily pull off in order to neutralize our compound. Because we have two carbon groups here, that's not going to happen. There's no just like grabbing this stuff to make it neutral. What we're instead going to have to do is, because we have nitrogen and nitrogen is also a base, what it can do is it can pull off a proton to do kind of like an elimination. We're going to pull off one of these. Typically, you're more substituted protons just because you're dealing with a secondary nitrogen. It's going to be a large base. These are never really small bases. So if we pull off this proton here, we can make a new double bond, kick the current one out to the nitrogen. In order to make what's referred to as an enamine. I'll give you guys a second to finish writing this down. So, bit of a review of all these reactions. We've got H plus and water. Gonna make our gem diol. H plus and alcohol. It's gonna make our acetal. H plus and diol here is gonna make our cyclic acetal. H plus and thiol is going to make our thioacetal. Our dithiol can make a cyclic thioacetal, throwing in Raney nickel. Can make just carbon. H plus and a primary amine. Can make an imine. and then H plus in a secondary mean. Can make an enamine here. So these are all these reactions that kind of use a very similar mechanism. They all kind of go through the same stepwise. You protonate, you have something come in and attack, you do a proton transfer, you kick out water, and then either forming one of these products through a couple of different ways will get you to your final answer. Okay, we are going to take a break here. There are technically two more of these that we'll go through. They're just different versions of these amines where you have like an oxygen or two amines on there. But they'll take like 2 seconds to talk about when we get back. So let's come back at 10:08 and we will go through the rest of chapter 19. All right, so let's get back to it. We're going to talk about two more of these that are, I'm not going to go through mechanism, they're basically identical. If you take a hydrazine, which is just two amines, we're just going to kind of ignore one of them is the easiest way to describe it. So what this is going to give us is an imine with just nitrogen still attached to it. And you can essentially act like one of them doesn't exist. This does have a reaction that accompanies it where we can reduce off a carbonyl, so similar to the way we can with a cyclic thioacetal. If we add in KOH, water, and heat, this can also be reduced down to just our hydrogens. Similarly, we can make what's referred to as an oxime. If you have both nitrogen and oxygen, the nitrogen is the better nucleophile. So I like to kind of put these two together. And we're just going to basically treat the oxygen like it's a carbon group. So along for the ride. So pretty straightforward. Nothing too special about these two. Something to mention is that all these reactions are reversible. If we add an H plus in water, it takes a little bit of special equipment, but we can essentially drive these all back to our ketone. And this goes for all of the reactions we've covered today. So like our cyclic acetals and things like that. We're not going to go through a specific mechanism as to how this happens, but it's essentially the reverse of what we've been doing. At the end, you have to evaporate off the water, or else you'll end up with gem diols. Let's just go backwards for all these reactions. Okay, so let's talk about some reactions we've kind of done before, which would be some carbon nucleophiles. Or actually, first, let's do one reaction that lets us make an amine. So when we make these amines, they're fairly stable. So like if we take a carbonyl and throw an LAH, this will get reduced down to an alcohol. You can do the same thing with an imine. And this is the way to make amines. So we can do this reduction, same reduction we were doing before, just with nitrogen as opposed to oxygen now. So let's talk about some carbon nucleophiles. These are reactions that we've mostly done before. So the first one is just a Grignard. Taking ketone or an aldehyde, throwing in propyl Grignard here. Select as nucleophile, but also reduce our reaction, so end up with an alcohol, as well as the addition of this propyl group. We can also do this with a nitrile. So if we take HCN, we can pick up this H here, and then our CN can come in and do an attack. To add a nitrile here. We can also do the same reaction we did above, where we add an LAH after this point. So a nitrile can also be reduced into an amine. So throwing an LAH with a nitrile or an imine will let us get to amines. All right, so we're going to move on from these and start talking about what's referred to as the Wittig reaction, which is spelled with a W. But pronounced like a V. And I usually like to tell people that they're kind of like a reverse O's analysis. So if we think back to, what was that, chapter 9? Oh, maybe chapter 8. Chapter 8, if we throw in some sort of alkene here with ozone and DMS, we're able to cleave this. Into 2 carbonyls. What we're going to be doing is going to be the opposite. So we're going to be taking a carbonyl and what's referred to as a gilid. But somewhat similar structure, combining these two together in order to make an alkene. So going in the opposite direction, we're taking 2 compounds, adding them together in order to make the alkene, as opposed to the ozonolysis where we're breaking it down. So kind of the opposite of that. The way that these work is we're going to start with some sort of haloalkane. And we are going to add in triphenylphosphine. This is going to act like a nucleophile. It's going to do an SN2. From here, we can throw in a really strong base, which is going to be N-butyllithium. This is essentially just carbon as a base. it's going to immediately pull off one of these protons and give us what's referred to as a YLID. Why they picked that word, I have no idea. These are fairly reactive. We can throw them in solution with any sort of ketone. And it is going to generate a new carbonyl between both ends of this molecule here. So we get the two benzenes with the carbon in between them. From the left part, we get the 3 carbons from this YLID here, and that would give us this product here. So let's talk about how this exactly works. It's a pretty straightforward mechanism. YLIDs are kind of the opposite of what you expect from a carbonyl. So when we think of a carbonyl, we think of our oxygen being the more electronegative molecule, having a resonance structure where we can push up these electrons away from the carbon to the oxygen. Getting a positive here and a negative here. With the YLID, our carbon is actually better at holding the negative charge. So what our resonance structure is going to look like is our electron is going to go down to the carbon. Look at the arrowhead. To give us this here. And then from this point, we are going to form a 4-membered ring. So you can either draw that from the resonance structure or the regular structure. I'm going to draw it from the resonance structure. So this is going to attack the positive, and then our negative up here is going to attack this positive. We would make this 4-membered ring structure. It is going to quickly fall apart. So these electrons are going to come down to make a double bond. These ones are going to come up to make a double bond here, and we're going to end up with triphenylphosphine oxide, as well as our Wittig product, where we merge the two together. 2 double bonds in order to make basically a larger double bond. This is always going to favor the Z form, actually. Which is somewhat interesting. So if we take, let's go back to that last example, but we're going to make it asymmetric. this Z alkene will actually be our favored product. A lot of that has to do with the actual mechanism of it forming. We're not going to spend too much time on it, but I just kind of want to touch on it. All right, we have one more reaction to talk about, and then we will be done with new material for this exam. And that is a reaction called the Baeyer-Villiger oxidation. And this is going to be a reaction where we use something like MCPBA again. On a ketone. So if you take a ketone and you throw an MCPBA, yeah, not draw an arrow. This is going to do what's referred to as an oxygen insertion. And it's going to let us transform a ketone into an ester. There is kind of a priority chart of this. So in terms of, there's always two sides to your either ketone or aldehyde when you're doing this reaction. For instance, for this ketone, we have a tertiary and a secondary center. The priority list for doing these is going to start off with the proton is the most likely side to insert this on. I'm going to talk about that in a second. So that'll be things like aldehydes, followed by a tertiary center, followed by a secondary center, followed by a phenyl center, primary, and then methyl. Although primary and methyl is the same thing in this case. So really just primary. So for this compound here, if I add an MCPBA, I've got a tertiary and a secondary. Taking a look at our chart, it should favor adding to the tertiary side first. So it's going to insert an oxygen here, and then we need the rest of our molecule, giving us this structure. We said aldehyde is the most likely, or sorry, proton is the most likely, so if we have any sort of aldehyde, this is going to immediately insert into that proton bond and just make a carboxylic acid. What am I doing? Oh, sorry. Making carboxylic acid here. And then one of the more interesting ones is that we can use this to make esters on aromatic rings. So we listed phenyl here. This is going to refer to as if we have something like this ketone that is next to a benzene or benzene ring if we add an MCPBA. Because phenyl is higher than primary here, this is going to be able to insert and generate a ketone. We can use this alongside LAH. And that's going to let us generate an alcohol. So if you reduce this down, we can make a phenone plus ethanol here. So this is going to be a particularly useful reaction when it comes to some synthesis problems. So we're going to spend the rest of the time kind of talking through a couple of different ways to do some synthesis problems. There was an extra worksheet. We're going to go through a few of them, but not all of them. I'll give you guys a little bit of time to attempt some. And then we can talk about them together. I'm going to take them, I'm going to modify them a little bit. So this is a quicker way to make an alcohol than some of the other ways we've talked about, especially kind of going back to some chapter 18 reactions. Ways to make alcohol. We could go through our entire diazonium pathway. We could chlorinate. Add in a nitro group. And then add an NaOH, but then we still have that nitro group on there. So this is by far the simplest way to do it. We can do it in 2 steps. I guess 3 steps. So we'd add some sort of carbon group. Followed by MCPBA. And then we could reduce it off with LAH. So alcohols aren't the easiest thing to make. There are a couple of different ways to make them. So just kind of throwing some of them out there. I'm going to give you guys a few synthesis problems to kind of work through. And then we'll talk about them. I'm just going to throw one of them up there, give you guys about 5 minutes, and then we'll talk through it and I'll give you guys another one. So let's start with, I'll just draw it down here. So hard line. I can redraw it higher up in a minute. Let's start with making this compound here. So I'm going to give you guys about 5 minutes. We'll be back at 10:39 to talk through some different possibilities for making this. So I will Talk to you guys in a minute. All right, so taking a look at this, we got a couple of different components here. I'm going to do this mostly through a Bayer-Villiger way because that's going to be kind of our easiest one. Um, Most likely adding our alcohol first is going to avoid any complications. If we end up with both ketones on there at the same time, that could be complicated because you're not going to be able to selectively reduce or oxidize one of them. So let's start off by just adding one of them. And to give you a sense of what I mean, I'm drawing red. If I was to now add the next one, I'm going to run into a problem where if I add in my Bayer-Villiger, there's no selectivity between the two of them. So then when I try to reduce the LAH, I can't pick and choose. They're both going to do the exact same thing. I'm going to run into the same problem on both ends here. Both of these are just going to make alcohols. So what I need to do is basically completely work with one side and then do the other side later. If we add an MCPBA instead first here, before we have the other ketone on there, also this is a meta director, so it wouldn't even form there, it would form here. So that's going to cause another issue. But let's go over here. We had MCPBA. We can now reduce the LAH. This lets me generate my alcohol. It's a group 1. It's going to be an orthopara director. If I, at this point, I could form my other ketone without any issues. So adding into solution. I'm going to erase some of this red pathway. From here, we can either do the chlorination now or we can do the MCPBA now. It doesn't really matter which one we do next. We have a group 1 and a group 5. We're going to be favoring our group 1. Ortho para director, but para is blocked. So if I add in Cl2, AlCl3, it's going to selectively go ortho because that's the only available spot. And then from here, if I add an MCPBA, again, this can take me to our final product. Any questions on this one? Okay, I'm going to give you guys one more. We'll go till about 10:48. We'll try to solve it. So, I will give you guys about, yep, so about 10:48. So we'll meet back then to talk through this problem. All right, this one's gonna be very order specific. In order to make an amine, I'm gonna have to go through some sort of imine. That sounded confusing. At one point in time, especially if I want to get these to add to the correct positions. I'm going to start off by adding, these are kind of reverse arrows to try to think about ways to go through this. I'm going to start off with this oxygen because it's going to give me an ortho or a meta director, which I think will be useful for adding that chlorine. So I start by just adding in that. I've got my meta director. I could chlorinate. the chlorine is now my highest priority group. That is a group 4 versus the group 5, which is the ketone. It's an orthopara director. If I look at its positions, the least substituted one is where this BR is over here. The other two are kind of getting blocked by the ketone. So if I brominate, it should add to that position. Oops, I want the product still there. From now, we just need to make an amine. So we can make an amine using the stuff we talked about today. So H plus ethylamine followed by LAH. All right. So that is all the material we're going to talk about in this exam. We might do a couple more synthesis problems tomorrow, just as kind of a little bit more of a review, as well as going over the practice exams or the previous exams for this class. So that is all I have for today. I will see you guys tomorrow.